All right, I hope you managed to digest the first lecture. I want to move on to the second, where we talk about functional localizers as well as periodic designs, both of which are really common and powerful techniques. And again, they make some important assumptions that aren't always, super obvious, so I just want to go through them. The idea with a functional localizer is that some parts of the brain may differ from one person to another for various reasons. It could be because the anatomy differs, it could be because of the way you grow up and your experience differs, but functionally they're equivalent to one another. So it's one thing to say, look, this piece of anatomy is the same as this piece of anatomy. I'm interested in those. That's fine. That's just an anatomical comparison. But you have parts of the brain that respond strongly to particular categories of stimuli, for instance, that vary in terms of where they're located within certain boundaries. And the classic example of that would be people's responses to faces. Brains like faces in humans and most primates, right? And one of the early demonstrations of this was some work that Sargent did in Canada and later was picked up by Nancy Canwisher in Boston. And she talked about an area in the fusiform gyrus in human beings that she referred to as the fusiform face area, okay? Because it was a robust response to faces independent of who you were, and it also varied a bit spatially. And we'll go through some examples of this, right? But the key here with functional localizers is you can use them for one of two purposes. Sometimes you can use them for both. And that is, we want to characterize activations. We want to understand what this area of the brain is doing or what part of the brain is responding most strongly in a more complex scenario. Or sometimes what you do is you just want to limit the multiple comparison problem. So that is to say, you want to say, look, this is a part of the brain that responds to this particular stimulus or this class of stimuli, and most of the rest of the brain doesn't. So what I really want to do is just focus in on the bits that really care about the stimulus and ignore the rest. And in order to do that, I need to functionally localize that to begin with. And the key is that you're going to do this in each individual subject so that you have something to use that's very specific and therefore targeted toward individuals. And that will improve your sensitivity to the activations that you're really interested in. Let's give an example of attribution. Okay, so this is a study that Van Duffel did, again, getting on to 20 years ago, that was really interesting. What he was interested in was how do people, and monkeys in this particular case, recognize 3D shape from motion. So if I just give you a pile of sticks, that's all it looks like when it's just not moving. But if it starts to rotate, then you can immediately see whether it has 3D structure or whether it's just a pile of sticks, right? But it's not until it starts to move that you can actually see that structure. And the question that Van Duffel was asking was what part of the brains were interested in this and were they the same or different when you did it in humans, whether you do it in monkeys. And the nice thing about this is an example of a study where you don't really need any particular measure of behavior. You kind of can't help but recognize the 3D structure if it's there, and that's true for both humans and monkeys. So what people were doing were they were passively watching these videos of moving lines, and in half the cases the moving lines reveal a 3D structure as they rotate, and in half they don't. They're just a random pattern of moving lines. But they all have the same sort of low-level visual dynamic characteristics. And what you're seeing in this map here is the activation in red-yellow for monkeys and for humans with respect to the parts of the brain and early visual cortices that were activated as a result of comparing 3D structure to these just random moving lines that don't give structure, okay? And it's really hard to compare between the human and the monkey to know whether they're the same or different if all we have is the anatomy. In part because the anatomy varies from species to species. Humans have, like 2 gyri on the ventral surface of the brain, whereas monkeys only have 1. And the links between the gyral anatomy and the function aren't very clear. They vary from individual to individual. So this is a case where Van Duffel used functional localizers to map visual structure in the brain, and this is something that we talked about in week 1 with Marty Serino's brain mapping, and I'll revisit in just a few minutes. But what he allows you to do is map out the difference between V1, V2, V3, V4, etc. And you can see that on those lines. They've been marked in, so you can see where V1, V2, V3, etc. are, because in this individual, in the monkey and in the human, Van Duffel did this functional localizer in order to specifically localize those boundaries in that person or that monkey. And what you can see is that V1 doesn't really care what the difference is between whether you get 3D structure or not. In contrast, V2, V3, V4, as well as parts of the motion complex, like MT, are showing significant activations. And that's true in both the monkey and in the human. So you can see this activation in the monkey, which I'll illustrate in the video, and also the same pattern in the human. But what's really interesting is this area of the intraparietal sulcus, which is shown in this dotted purplish kind of line, because there is basically no activation in the monkey in that area, whereas the corresponding areas in the human show significant activation in quite a few parts of the intraparietal sulcus. So there are both commonalities and differences with respect to the way monkeys and humans activate in response to extracting 3D information from motion. But there'd be no way to explain that or even know for sure that was the case if they hadn't conducted these functional localizers so they could say, yep, these specific regions are showing commonalities, these specific regions are showing differences. And it's not due to differences in the anatomy, it's down to the actual function. Another example I gave earlier was a study that Arlene Cordillo did, where she was interested in what was happening when people were listening to sentences of different sorts. And if you recall, what she had were blocks of forward sentences followed by blocks of digitally reversed sentences that just don't make any sense. And when you compare what's going on in the brain from the forward sentences to the reverse sentences, you get this pattern of activations here, which shows parts of the brain that are interested in processing the sentences. Now, she then can say, look, I can look at the areas in red and ignore the large swaths of the brain that aren't in red because they're not interested in sentences. When I get to the more specific event-related comparison that she had, where she was looking at how congruent, neutral, and incongruent sentences are processed, right? And you can see that by doing that, she's increased her statistical sensitivity or power by a lot, because rather than doing like multiple comparison corrections over the whole brain, she's now only doing it for the area that's interested in sentence processing. And because that comparison is orthogonal, independent, she's introduced these constraints that make her statistical sensitivity power greatly improved. So as I said, I wanted to talk about what's called the fusiform face area because this is the classic example of how to do functional localizers. And this is an experiment that Nancy Canwisher's group did a few years ago. And what they do is they show these videos of people's faces versus videos of objects or videos of like houses and scenes. And when you compare them, then you see significant activation in the fusiform gyrus, which is shown here in this sort of red-blue on the left in 4 different individuals. And the importance here is that depending on your confidence in ventral occipital temporal anatomy, you can probably recognize that these are not in the same exact locations. All of them are in the fusiform gyrus, but they vary from person to person. So it's not like you could say, well, I'm only going to go to this bit of the fusiform gyrus, because if you do that, you would miss out some participants who were in different parts of the fusiform gyrus. So it's really important to have functionally localized it so that you can say, look, the area that I'm going to look at is specifically the area shown here by these arrows in each person, because functionally that's the same from person to person. That's the area that cares about faces in their fusiform gyrus. And she then ran a second experiment where each of these participants saw just a range of different types of face stimuli, which are what are shown on the right. So things like full frontal views of faces, profile views, funny kind of moony faces, non-human faces like cats or cartoons, faces that are upside down, faces that are missing parts, etc., right? And the nice thing is, within the area that she had already identified as the fusiform face area, she could extract the bold signal to all of these different kind of stimuli and just sort of compare the strength of the signal. And that's what those numbers are. So, for instance, if you show somebody, a front-on face versus the back of the head, the front-on face is giving you a signal that's about twice as large, 2 compared to 1, right? Whereas if you show somebody sort of a horse that's had its head taken off, it's even smaller than that. And you get this kind of gradation in terms of responses. And you can see that the strongest responses are to normal faces. It's less strong if you show other species faces or cartoon faces, etc. But it's a way of being very detailed in characterizing the information processing, because you can test a whole slew of categories. and you can be confident that this is the bit of the brain that was responding to faces. So I'm only going to query this bit when it comes to how strong does it respond to these other categories. There are a number of design implications to doing this, right? And one of the ones that's received a lot of attention is whether or not the functional localizer should be done as independent runs or it should be part of a factorial design. So for instance, in the Canwisher example and the Van Duffel examples that I've given, both of them collected their functional localizer data as independent runs. They run their functional localizer scans for the participants, then they run their main experiment with the participants. And that's absolutely fine, right? But other people try to design the functional localizers into their experiment. And for instance, that's what Cardillo did. By making the contrasts orthogonal to one another, she was able to make sure that she just ran one experiment where the functional design was the functional localizer was one contrast, and the contrast of interest were a second contrast, but that were independent of one another. That was that they were orthogonal. But there are some other things that are talked about a lot less that I think are really important and worth discussing. One of which is, if you are going to do independent runs, how reproducible are they? Because a key assumption is, in your independent run, you've identified this patch of cortex, and this patch of cortex is the right bit. But if you had run a second run, and you had gotten this patch of cortex, well, wait a second, that's really bad, because it's got to reproduce. The assumption is that you're really looking at the right spot. How good are our functional localizers of identifying the right spot? And then related to that is, well, does it depend on how much data you have and how you analyze the data? Like, I mean, if you just collect a ton of data, you might think, okay, well, that's going to converge on the right spot. Whereas if I just collect a short amount of data, maybe it's going to be a little bit more variable. And that's important when you're thinking about designs, because if all you care about is localizing this region and doing it quickly so that you can get onto your main experiment, you don't want to collect an hour of functional localizer data before somebody does a 10-minute experiment, right? That's just the wrong balance. You want a small functional localizer that then you can collect most of your time doing the main experiment of interest. So how accurate are those assumptions? Well, this independent versus factorial design issue was a debate that played out between Carl Friston's group and Rebecca Sachs, Nancy Canwisher. The key papers are cited here. I highly recommend that you read them because they address different assumptions, but they're essentially what we've said, right? Do you want to have an independent localizer and then a main task, or do you want to build them in together? And the reasons that you would want an independent localizer is because sometimes not everything's like a fully factorial design. So the example that I gave about looking at activations in fusiform face area is a good example of that. There were, I don't know how many conditions, probably a dozen conditions that Canwisher was testing. And she didn't want to have a dozen conditions sort of with and without faces, because those dozen conditions without faces aren't even interesting. That's just wasted time, right? So she could do the independent localizer with faces versus objects, for instance, and then she runs the main experiment where she tests all the conditions of interest. And it's not a factorial design, so she uses an independent run. In contrast, the Cardillo experiment used a factorial design where she could build in this orthogonal contrast, and she puts them all together. The nice thing about doing that is, by definition, in the data that she collected, she identified the parts of the brain that were sensitive to listening to sentences and understanding sentences. So there's no issue about reproducibility, like whether that would be true if she did it again for those subjects, because she didn't run a separate experiment. She's only using those data in order to answer her question, so she doesn't have to worry about some of the reproducibility issues. If you are doing it as independent runs, then you really do have to care about reproducibility, because your assumption is that you have functionally localized the right spot, okay? And if you were to run the functional localizer again in the same person and get a different result, then that assumption is not being met, right? And this is some data that Keith Duncan did along those lines, where he was looking at functionally localizing the so-called visual word form area, that place that Dehaan localized as on the ventral occipital temporal border that's sensitive to written words, right? So he used a simple contrast, people reading words versus people looking at a fixation cross. And you see that across individuals, there's a lot of activation in these parts of the brain. But what's interesting is he ran the individuals twice. He ran them in one 10-minute functional localizer waited a minute, and then ran the same people in a second functional localizer that was essentially exactly the same. And what he did was said, well, how close are the functionally localized spots in individuals? And does it matter on how statistically rigorous I'm being? So if I'm being really lenient, you might think, well, the overlap's going to be really poor because, there's a lot of false positives in that. Whereas if I'm being really rigorous, I've really identified the right spot, and that should be the same right spot from run to run. And in fact, that's not what he found at all. He found just the opposite. And you can see that down the sort of y-axis of the page here. If you use a statistically lenient threshold, a z of 1.64, then you're getting nearly 2/3 overlap from run to run when you identify this area. In contrast, if you use a really rigorous threshold, a z of 5, which would, for instance, correct for the fact that you're doing multiple comparisons across the whole brain, then you're down to only 1/3 of the voxels showing an overlap. So that is to say that if you were to identify this region using a rigorous statistical threshold in a short run, 10-minute run, then you can assume that if you did it again in the same person, literally only 1/3 of those voxels would be the same. So therefore, when you go to use that as your region of interest, when you analyze your data, you've got a real issue because you're analyzing potentially very different activations, right? Because they're coming from independent functional localizer, independent data sets. So this just raises an interesting question, which is, okay, wow, that's really worrying. Is it because we're just not collecting a lot of data? Because functional localizers tend to be super quick, is it because we're doing 5 to 10 minutes of data rather than collecting enough data per person? And again, Keith Duncan looked at this. I'm stepping ahead of myself, sorry. So this is the consistency plotted as a bar plot instead, and you can just see it goes down from 60-some% down to about 30%. And it doesn't really matter whether you're trying to identify words in that visual word form area or whether you're identifying objects in the lateral occipital temporal complex. You're getting the same exact pattern. The specifics vary, but it really matters that you use a lenient threshold if you're using a small amount of data. And that's done in terms of overlap, which is the key thing for identifying, using a functional localizer. You want to identify all of the voxels that are involved in this area. But you could do it a slightly different way, and you could say, well, what about the peak? What if you just give me the peak response, and I just draw like a little sphere around it, because that way I don't care about the specific voxels. I'll do something that's really meaningful, which is the strongest response. And that's what's being plotted in this. This is the peak response in terms of how far apart they were from person to person in run 1 to run 2. And you can see that, for instance, for words, when you functionally localize that visual word form area, they're like 1.4 centimeters apart, down to about 6 to 8 millimeters apart. At their best, when you collect a ton of data, like an hour's worth of data, you get it down to about 7 to 8 millimeters apart. It's a little bit better for objects in the lateral occipital complex. With an hour's worth of data, you get it down to about 0.5 centimeter from one another. And if you look at faces, it varies a lot depending on whether you're looking at the left or the right fusiform face area. In the left hemisphere, which is the non-dominant hemisphere for faces, if you collect like an hour's worth of data, you actually get pretty robust peaks that don't vary that much, less than 2 millimeters. In contrast, in the right fusiform face area, which is the classic fusiform face area, you get these differences that bang around 8 millimeters. So that is to say, even with a lot of data, looking at the peak response is not a good way to functionally localize because there's quite considerable variability on the order of a centimeter, which is a lot in FMR terms, across runs. So this is a complicated plot, but this is how you look at what happens, when you trade off the amount of data for the statistical rigor. So on the x-axis, you're looking at a small amount of data. 32 scans is like sort of on the order of 5 minutes of data, all the way up to 280 scans, which is closer to like an hour of data. And on the y-axis, looking about how consistent it is. And you want that number to be as close to 1 as possible. In a perfect world, you'd like it to be 1. It's just perfectly consistent. But as you can see, it never is. And then there are two trends that are worth noting here. That one is that if you use more lenient statistical thresholds, the blue, like the top blue line here, 1.64, or this red line, then you get peaks in consistency with small number of scans, sort of on the order of 10 minutes of data collection. In contrast, if you use a rigorous threshold, that sort of cyan, light blue that's labeled 5, then the more data you collect, the more consistent your answer is. So that is to say, there are two ways to go about using independent functional localizers that maximize your consistency. One is collect a reasonably short one, something about 10 minutes, but if you do that, then use a very lenient statistical threshold in order to identify your region of interest. Or, if you want to be really rigorous about it, collect a ton of data, put them in there for an hour just to functionally localize, and then use a whole brain correction, a statistically rigorous correction. And either way, you're going to get something on the order of 60 to 80% consistency, which is still far less than the assumption that you've identified these voxels and they're the right voxels, right? That would be an implicit assumption that the consistency is just 1, and it never is. So I've kind of gone on and on about functional localizers a bit because they're a very, very simple concept, but there are some complexities in terms of the way you actually use them, and that really affects the way you design your experiments. The other thing I want to talk about are what are known as periodic designs. And this is a different kind of approach altogether. So a periodic design is used to identify spatial maps in the brain. So that is literally physical maps that play out on neocortex or even subcortical structures, such as retinotopic maps, tonotopic maps, somatotopic, etc. And the way you do that is you're going to repeat a sequence or a series of stimuli over and over again in a cycle. And that cycle is going to allow you to look for standing waves in activation in the brain that you can allow you to identify the parts. So let me just talk you through this image. This is a map of visual cortex, like primary visual cortex in humans. And the primary visual cortex is located deep in the calcarine sulcus, which is in the back of the brain, sort of in the occipital lobes. And you can see that the top circle here sort of shows two things, more than two things actually. It's complicated, but let's just focus on two things. One is that the darkest areas that are labeled 1, 2, 3, and 4, those are the foveal areas. That's the middle bit where you have the highest acuity of your vision. And then outside that is the parafoveal, which is the sort of lighter gray. And then outside of that is the periphery, which is the sort of more white kind of areas labeled 9, 10, 11, and 12. Okay, so there is a spatial organization that goes from foveal to parafoveal to peripheral vision. And you can see that in terms of that line, that set of circles. The other thing that's worth pointing out is that there are spatial patterns here. So for instance, the numbers 1 and 3, 5 and 7, 9 and 11, those are on the top part of the image, but they go to the bottom part of your calcarine sulcus. So for instance, you can see that hopefully on the plot below, all those odd numbers are below the calcarine fissure. In contrast, all the even numbers, which are the bottom part of your image, go to the higher part, like literally a more superior part of your brain on the superior edge of the calcarine fissure. So there is this kind of spatial pattern, and if we wanted to sort of identify those regions in a human being, we can take advantage of this. And the classic way to do that is to use a combination of eccentricity and polar angle mapping. So the idea here is, let's start with that first point, that you start with the focus and it expands out to the parafovea and then it expands out to the periphery. Well, if you give people a stimulus, like this circle that's shown in red on this green area, that starts in the fovea and then expands out. So assuming it was actually big and it was getting to your parafovea and your peripheral vision, then you can see activation in here as like a white line, a wave that starts deep in the calcarine fissure and is actually expanding out through the parafoveal and the periphery. Okay, so by repeating this stimulus in this cycle, inside out and then back to in and out, you get this kind of repeating wave of activity that allows you to identify where those parts of visual cortex are. You can do the same thing with polar angle. That is to say that if you have this kind of little pie wedge that's rotating around, it's rotating through the upper visual field, through the bottom part of your calcarine sulcus, and now it's gone to the lower visual field in the upper part of your calcarine sulcus. And you can see that there are waves that are meeting each other. That is to say, there are waves that are coming together, and that's going to show you the difference, the borders between, say, V1 and V2, because that's where the retinotopy reverses. So you can use this, and this is an image I showed you in week 1 from Marty Serena, who first introduced this technique, this combination of eccentricity mapping, which is shown at the top, and polar angle mapping, which is shown at the bottom, using the kind of stimuli I just showed, to identify the borders between V1 and V2, V3, etc., and V4. So V4, for instance, is present in the more ventral part of visual cortex. There's not really a dorsal V4. It's not really the same thing. But V1, V2, and V3 have both ventral and dorsal components, and you can see that in this map. So V1 plus, for instance, refers to the higher part of the visual field for V1, whereas V1 minus is the lower part of the visual field. And in between, what's been cut there is the calcarine fissure. So this is a method for identifying literally spatial maps in the brain by repeating these cycles and making sure that you can see these repeating waves of activation. And of course, this isn't really limited to visual processes. You get these maps in other areas such as auditory cortex. This is an example of tonotopy in primary auditory cortex. In primates, primary auditory cortex is typically divided into 3 regions, A1, R, and RT. And they normally go from posterior to anterior parts of, for instance, the Heschel's gyrus in humans, but the corresponding superior temporal gyrus in other species. So A1 is the most posterior, R is slightly more anterior than that, and RT is even more anterior to that in a macaque, for instance. So that's what's shown here, and you can see that these frequency gradients are shown as the colors from low frequencies in red through medium frequencies in yellow, green, all the way up to higher frequencies in the blue colors. And what you can do is you can do the same thing. Instead of doing like annulus that started at the middle and expanding out, that is an expanding circle, or a rotating pi wedge. In this case, what you're going to do is play frequency sweeps, play low frequency sounds, and then a little bit higher frequencies, and then medium frequencies, and then a little bit higher, and all the way to high frequencies, and then repeat, right, and repeat. So you get this same kind of standing wave of activation that allows you to look for where there are differences in these different auditory areas. So for instance, where A1 switches to R, because you can see from the image above, there's a reverse pattern there. And what you can see is actually in humans, and this is some work that was done in 2014, but there have been versions that came earlier. I just thought this was a really nice illustration of it. There are low frequency responses in the more anterior part of Heschel's gyrus, this site of primary auditory cortex in humans. And as you move back in the brain along Heschel's gyrus, you get to higher frequencies, but also as you move more medially in the brain. So there's a gradient here, but it doesn't follow exactly the same pattern that you see in other species, which is consistent with the fact that the anatomy isn't quite the same in humans as it is in other species either. Instead of getting something that goes from high to low to high, which is what you'd see on a macaque, for instance, we actually have a high to low to high, but it's not just going forward, it's coming from the back to Heschel's gyrus, and then from Heschel's gyrus to the more medial part of Heschel's gyrus within the sylvian fissure. And then this was an interesting study. I just picked it up because I thought it was pretty cool. This is a study where they're looking at somatotopy, but they weren't looking at it in like somatosensory cortex, where you would expect it, but in a different part of the brain. In this case, they were looking at it in parts of the cerebellum. And the cool thing here is that the cerebellum has a very, very fine structure. So in order to get this information, they had to go to very, very high resolution fMR. These were scans done on a 7T scanner, and they used 1.2 by 1.2 by 1.2 millimeter voxels. Normally we would use like 3 by 3 by 3. So these are like 20 times greater resolution. And in order to do that, they needed to take advantage of the greater signal to noise in like a high field scanner, like a 7T scanner. And what they did was they had people in the scanner, and they just had their hand out basically, and there was an experimenter who had headphones on that were compatible with the scanner, and whenever they heard a beep, they would sort of rub the fingers from the tips down to the knuckles, down towards the base of this part of the knuckle, and then they'd repeat, and they'd just sort of do this, and then there would be another beep, and they would stop, and then they would do it again for the next 2 fingers, etc. So they're getting this kind of manual stimulation that's going from the tips of the fingers down towards the knuckle, and it's repeating. It's done in the same cyclic pattern. And what you can see here is that it's not super beautiful, but if you color code the fingers such that the thumb is blue and the pinky finger is red, you can see this spatial pattern where the blues fade into the index finger, which fade into the middle finger, and then the pinky and the ring finger are actually reasonably co-localized. They're pretty closely linked with one another, so it's a little bit harder to tell them apart just from the scan. But this is a beautiful study that was done taking advantage of this kind of periodic design in order to map somatotopic organizations in an area of the brain that you may not have expected somatotopic organizations. So what are the implications of using a periodic design? Well, the first thing is that this is the one that's truly different from what we've talked about so far. A periodic design is neither a blocked nor an event-related design. It's its own thing. And in that sense, it's why I've tried to classify it as a more advanced design. One of the things that happen is that if you constantly repeat a cycle in the same way, then again, you get all of those order effects that we talked about in week 2. So it's really important that if you're going to do a cycle, you not only run it forward in some runs, you run it in reverse in other runs to make sure that you're counterbalancing and avoiding order effects. Where they're in common, which is effectively a conjunction, is where the true topic organization is, the structure of the map is, okay? Doing these kind of studies typically requires a ton of data. They normally collect like about an hour's worth of data to get these kind of maps. And that's because of this variability and reproducibility. The fact of the matter is it's sometimes hard to tell whether or not you've collected enough data. So rather than chance it, they normally do it in a small number of subjects, but they just collect a ton of data from them in order to make sure that the data are very robust. Which, if you recall, was one of the possibilities that I suggested was a good way of using a functional localizer. And then the other thing that I'm just going to mention, and we can talk about it a little bit later, is that this kind of design uses a different analysis altogether than the things that we're going to talk about in this module. So we're going to talk about using the general linear model and using a sort of mass univariate approach, but instead what we're going to use for a periodic design is a Fourier analysis. We're interested in the phase of those cycles because that tells you where in space your representation is, and that is an altogether different way of analyzing your data. Nothing wrong or right in one of them. They're just different ways of analyzing the data to ask different questions.